In this section, we will discuss the operation that the system must provide for managing processes. These operations include process creation, process termination, and other action that affects the state and behavior of the processes. Process creation is the operation that allows the system to create a new process. A process can be created by another process called the parent process or by the system itself. The parent process can specify the attributes and resources of the new process, such as its priority, memory space, and file descriptor. The new process is called the child process, and it inherits some of the attributes and resources of the parent process. The parent and child processes can communicate with each other through various methods such as shared memory, message passing, or signals. A process termination is the operation that allows the system to end a process. A process can be terminated by itself or by other process or by the system. A process can terminate itself by executing a system call such as exit or return. A process can terminate another process by sending a signal to it such as kill or abort. The system can terminate a process for various reasons, such as exceeding its resource limit, violating security policies, or encountering an error. When a process terminates, the system releases its resources and removes it from the list of active processes. Other operations on processes including changing the state of a process, suspending or resuming a process, changing the priority of the process, and transferring control from one process to another. These operations are useful for implementing various features and functions of the system, such as scheduling, synchronization, concurrency, and inter-process communication. We will discuss this topic in more details in the following slide. This slide explains how processes are created in an operating system. A process is a program that is executing on the CPU. Processors can create other processes using system calls such as fork or exec. The process that creates another process is called the parent process, and the process that is created is called the child process. Processes can form a tree structure where each node is a process and each edge is a parent-child relationship. The root of the tree is the first process that is started by the operating system, usually called init or systemd. The slide shows an example of a tree of processes in Unix. The root process is systemd, which has a process identifier or PID of 1. A PID is a unique number that is assigned to each process by the operating system. Systemd creates several child processes such as login-d, Python, and SSHD. Login-d is a process that manages user login session. Python is a process that runs a Python script. SSHD is a process that handles secure shell connection from remote host. Each child process can also create its own child processes. For example, login-d creates a bash process, which is a shell that allows the user to execute commands. Bash has a PID of 8416 and has two child processors, which is the PS and the VIM. PS is a process that displays information about the current process. VIM, on the other hand, is a process that runs a text editor. SSHD also creates another SSHD process, which has a PID of 3610 and handles a specific connection from a remote host. This SSHD process creates TCSH process, which is another shell that allows the user to execute commands. This slide illustrates how processes are created and organized in an operating system. Processes are essential for running programs and performing tasks on the computer. When a process creates a new process, there are some options for how the resources of the parent and the child are shared. Resources include memory file, devices, etc. The resource sharing options are: first, parent and children share all resources. Here, this means that both the parent and the child can access and modify the same resources. For example, if the parents open a file, the child can also read and write to that file. This option allows for easy communication and coordination between the parents and the child, but it also requires careful synchronization to avoid conflict and error. Second, children share subset of parent resources. Here, this means that the child inherits some of the resources of the parents, but not all of them. For example, the child may inherit the parent's environment's variables, but not its open file. This option allows for some degree of communication and coordination between the parent and the child, but it also reduces the potential for conflicts and error. Third, parent and child share no resources. Here, this means that the child has its own copy of the resources of the parent. For example, the child may have its own memory space, its own open file, its own devices, and etc. This option allows for complete independence and isolation between the parent and the child, but it also requires more overhead and duplication of the resources. Another option for process creation is how the parent and child execute. The execution options are, there are two here, which is parent and children execute concurrently, or parent waits until children terminate. Let's see the first one. Parent and children execute concurrently. Here, this means that both the parent and the child can run at the same time, either on a different processor or by switching between them. For example, if the parent creates multiple children, they can all run in parallel with each other and with the parent. This option allows for faster completion of tasks and better utilization of the resources, but it also requires more scheduling and synchronization. The second, parents wait until the children terminate. Here, this means that the parents stop running until all of its children finish their execution. For example, if the parents create a single child to perform a specific task, it can wait for the child to complete that task before resuming its own execution. This option allows for simpler control and coordination between the parent and the child, but it also reduces concurrency and performance. This slide explains how a process can create another process using the fork or exec system call in Unix. A process is an instance of a program that is running on a computer. A process has an address space, which is the memory allocated for the program code and data. When a process wants to create another process, it can use the fork system call. This creates a new process called a child, which is duplicate of the original process called a parent. The child inherits the address space of the parent as well as other attributes such as file descriptor and environment variables. However, sometimes the child may want to run a different program than the parent. In that case, it can use the exec system call, which replaces the child address space with a new program. The exec system call takes the name of the program to be executed as an argument. The parent process can wait for the child to finish by using the wait system call. This blocks the parent until the child exits or terminates. The parent can also resume its execution without waiting for the child. The figure shows an example of how a parent process creates a child process using fork. Then the child process executes a new program using exec and finally exit. The parent process waits for the child to exit and then resume its execution. This slide shows a C program that creates a separate process in Unix using the fork and exec LP system calls. The fork system call creates a new process that is an exact copy of the calling process. The new process is called the child process, and the original process is called the parent process. The fork system call returns a value to both processes, which is the process ID of the child to the parent and the 0 to child. If the fork system fails, it returns a negative value to the parent. The exact LP system call replaces the current process image with a new one. The first argument is the name of the file to be executed, and the following arguments are the command line arguments to be passed to the new program. The last argument must be null to indicate the end of the argument list. The exec LP system call search for the file in the directories specified by the path environment variable. In this example, the main function first calls fork to create a child process. If fork fails, it prints an error message and returns 1. If fork succeeds, it checks the return value. If it is 0, it means it is the child process. The child process then calls exec LP to execute the bin/ls command, which is list the file in the current directory. If exec LP fails, it returns -1 and set error number to indicate the error. If fork returns a positive value, it means it is the parent process. The parent process then calls wait now to wait for the child process to terminate. The wait system call blocks the parents until any of its children have finished. The argument now means that the parent does not care about the exit status of the child. So after waits returns, the parent prints child complete and return 0. This slide shows how a C program can create a new process in Unix system using the fork system call. A process is an instance of a program that is being executed by the CPU. A process has its own address space, which is the memory allocated for its code and data. When the fork system call is executed, the operating system creates a copy of the current process and assigns it a unique process ID, or the PID. The original process is called the parent process, and the new process is called the child process. The parent and child processes are identical in every way except for their PID values. The fork system call returns the PID of the child process to the parent process and returns 0 to the child process. The parent and child processes can then execute different parts of the code based on their PID value. For example, in this program, the child process used the exec LP system call to replace its address space with a new program, which is the Unix command ls. This command lists the file and directories in the current working directory. The exec LP system call takes the name of the program to execute as its first argument, followed by any argument that need to be passed to the program. The last argument must be null to indicate the end of the argument list. The parent process waits for the child process to finish its execution using the wait system call. This system call blocks the parent process until the child process terminates. The wait system call returns the PID of the terminated child process or -1 if there is an error. The parent process then exits using the exit system call, which terminates the process and returns a status scope to the operating system. This slide shows how to create a separate process through Windows API. A process is an instance of a program that is being executed by the operating system. So Windows API provides a set of functions that allow us to create and manage processes. The main function in this slide is the entry point of the program. It declares two variables, SI and PI. SI is a structure of type startup info, which contains information about how the new process should start, such as the window title size, position, etc. PI is a structure of type process information, which contains information about the new process, such as it handle, identifier, treat handle, and etc. The first thing the main function does is to allocate memory for these two structures using the zero memory function. This function fills a block of memory with zeros. The first argument is the pointer to the memory block, and the second argument is the size of the memory block. The size of SI is obtained by using the size of operator on its type. The size of the PI is obtained in the same way. The next thing the main function does is to create a child process using the create process function. These functions create a new process and its primary thread. The first argument is null, which means that the new process will use the command line specified in the second argument. The second argument is a string that contains the path and name of the executable file to run. In this case, it is a C/Windows/System32 mspain.exe, which is the pain program. The third and fourth argument are null, which mean that the new process and its thread will not be inherit any handles from the parent process. The fifth argument is false, which means that the handle inheritance is disabled. The sixth argument is 0, which means that no creation flags are used. The seventh argument is null, which means that the new process will use the same environment block as the parent process. The eighth argument is null, which means that the new process will use the same current directory as the parent process. The ninth and 10th argument are pointed to SI and PI structure, which will be filled with information about new process. To create a process function, return a Boolean value indicating whether it succeeded or failed. So if it failed, it prints an error message to the standard error string using fprintf function and returns -1 from the main function. If it succeeded, it proceeds to wait for the child process to complete. The main function uses the wait for single object function to wait for the child process to complete. The function waits until a specified object becomes signal or timeout interval elapsed. The first argument is a handle to an object, such as a process or thread. In this case, it is pi.hProcess, which is the handle to the child process returned by the createProcess function. The second argument is a timeout interval in milliseconds. In this case, it is infinite, which means that it will wait indefinitely until the object becomes signal. When the child process completes, it signals its handle and return an exit code. The wait for single object function returns when this happens and print child complete to the standard output stream using the printf function. The last thing the main function does is to close the handles to the child process and its thread using close handle function. The last thing that the main function does is to close the handle to child process and its thread using the close handle function. This function close and open object handle and free any associated resources. The argument is a handle to an object such as pi.hProcess or pi.hthread. So we move to the next slide. This slide explains how a process terminates and how a parent process can terminate its children processes. A process terminates when it finishes executing its final statement and it asks the operating system to delete it by using the exit system call. This is the way for the process to tell the operating system that it has completed its work and it does not need any more resources. The exit system call also allows the process to return a status value, which is typically an integer, to its parent process. The status value can indicate whether the process succeeded or failed or provide some other information to the parent process. The parent process can use the wait system call to receive the status value from its child process and perform some action based on it. When a process terminates, all the resources of the process are deallocated by the operating system. This means that the memory, file, devices, and other resources that were allocated to the process are freed and made available for other processes. The operating system keeps track of the resources that each process uses and ensures that they are properly released when the process terminates. A parent process may terminate the execution of its children processes using the abort system call. This is a way for the parent process to forcefully stop its children processes from running. There are some reasons why a parent process may want to do so, such as the child process has exceeded the allocated process, such as using too much memory or CPU time, and it is affecting the performance of the system or other processes. The other reason is the task assigned to the child process is no longer required, such as when the user cancels an operation or changes their mind. Another reason is because the parent process is exiting and the operating system does not allow a child process to continue if its parent terminates. This is to prevent orphan processes that have no parent and may cause problem in the system. The abort system call sends a signal to the child process that instructs it to terminate immediately. The child process may not have a chance to perform any cleanup action or return a status value to its parent. The operating system will deallocate the resources of the aborted child process as usual. In this slide, we will continue to discuss the process termination in some operating systems. Some operating systems have a rule that a child process cannot exist if its parent has terminated. This means that if a process ends, all its children processes must also end. This is called cascading termination. Here, cascading termination, it affects not only the direct children of the process, but also the grandchildren, great-grandchildren, and so on. The operating system is responsible for initiating this termination. The parent process can also choose to wait for the termination of a child process by using system call read. This call returns some information about the status of the child process and its process identifier, which is the PID. For example, the code PID equals to wait and status will assign the PID of the terminated child process to the variable PID and store its status in the variable status. However, sometimes the parent process does not invoke wait for its child process. So in that case, the child process becomes a zombie process. A zombie process is a process that has terminated but still occupies some resources in the system, such as its entry in the process table. A zombie process cannot be killed because it is already dead. Another possibility is that the parent process terminates without invoking waits for its child process. In that case, the child process becomes an orphan process. So an orphan process, we can say here, is a process that has no parent process to control or communicate with it. An orphan process may be adopted by another process, usually by special system process called init. In this slide, we will learn about the multiprocess architecture of the Chrome browser, which is a popular web browser developed by Google. Unlike some other web browsers that run as a single process, Chrome uses multiple processes to handle different tasks and improve performance and security. A process is a program in execution. It has its own code, data, and resources. Processes can communicate with each other through inter-process communication mechanism. Processes can also create new processes through a system called fork. The Chrome browser has three different types of processes, which is browser process, rendered process, and plug-in process. So let's see what each of them does. Okay, so the first one, the browser process, is the main process that manages the user interface, such as tab, menu, and toolbar. Here, browser process also handles disk and network input-output, such as downloading files and sending requests to web server. The browser process is responsible for creating and managing the other processes. The second process is the rendered process. It means that is the process that rendered web pages, which means it converts the HTML, CSS, and JavaScript code into pixels on the screen. Here, each web page open in a tab has its own render process. In this way, if one web page causes trouble, such as an infinite loop or a memory leak, then it will not affect the other tab or the browser process. The render process runs in a sandbox, which is a restricted environment that limits its access to disk or network I/O. This minimizes the effect of security exploits such as malicious code injection or data theft. The third one, the plug-in process, is the process that runs plugins, which are external programs that extend the functionality of the browser. Examples of plugins are Flash Player, Java Applet, and PDF Viewer. Each type of plugin has its own plugin process. For example, if you open two web pages that use Flash Player, then they will share the same plugin process. The plugin process also runs in sandbox to prevent security breach. So in summary, the Chrome browser uses a multiprocess architecture to improve its performance and security. It has three types of processes, which is the browser process, the render process, and plugin process, where each of them has a specific role and run in a separate memory space.